Okay, so thank you again for the invitation and for the opportunity to discuss our work here at IST, and again for the nice introduction, Katerina. So I'm going to talk about extreme plasma physics with lasers and in astrophysics. I'm going to focus more on the laser side, but I will like the key message that I want to convey to you today is that there are similar physics to explore with lasers that and in astrophysical scenarios, and now it's really a good time to work in this field and work in these problems. And I will try to show you what are the connections and what are the tools that many researchers are using to tackle some of these very exciting problems, both in the lab and in astrophysics. I would like to acknowledge my collaborators, and in particular the people at IST. I'm going to show the work of many different people. So I've had the privilege of working with very brilliant people, and I would like to acknowledge the work that has been done here at IST by all our team members, and of course the very fruitful and collaboration, friendship for many people around the world. My talk is going to focus on the prospects that numerical simulations have been triggering and have been creating for the past 20 years. And so I will show a significant amount of results based on numerical simulations that have been performed in different places around the world. But let's first start with a little bit of history. The terms associated with the extreme plasma physics or similar topics can be traced back to I would say a first paper by Gerard Roux and Don Umstader in Scientific American, and also on a report from the National Academy of Sciences in the mid 2006. On the frontiers of high energy density physics. And if you look at the title of this report is called Frontiers in High Energy Density Physics, and it's called the X Games of Contemporary Science. And the X Games, if you're not familiar with this is kind of an Olympic Games for extreme sports like skating and snowboarding and all that. So I think this is at this time there was this convergence on the side of lasers of extreme light, and on the side of high energy density physics, the exploration of these extreme scenarios. And this is what kind of tailored the concept of extreme plasma physics. There's a very nice recent definition of what is extreme plasma physics, and that I would like to go through here. This is a paper. It's on arXiv. It's actually called Extreme Plasma Astrophysics, but the description there also makes connection with the laboratory scenarios, but it really captures what this extreme plasma physics is all about. So this is plasma physics that is supplemented by several additional physics effects. And these are effects that you don't see on a classical textbook of plasma physics, and that would be considered exotic. So this includes special relativistic effects, both relativistically hot plasmas and relativistic bulk motions, radiation reaction effects, so scenarios where radiation is very strong and the radiation itself affects the dynamics of the system, electron-positron pair creation, and other QED effects, such as effects triggered by ultra-strong magnetic fields, and even GR effects. Of course, GR is not something that we expect to see in ultra-intense laser matter interactions anytime soon, but this is very relevant in relativistic astrophysics. So what I will try to show you today is that you'll find these evidences, these manifestations of extreme plasma physics in many different scenarios. I will focus on ultra-intense laser and particle beams, show a little bit of relativistic astrophysics, and if there is time, I can also show you an example on science fiction where extreme plasma physics can actually play a role. So the questions that we've been trying to address in our group can be stated in a very simple way. we are trying to understand what is the behavior of matter and vacuum at the intensity frontier. So intensity is on the order of 10 to the 23 watts per square centimeter, both in the laboratory and in astrophysics. And also what we've been trying to address is how can we understand and explore this complex and nonlinear behavior that is associated with these scenarios with a combination of simulations, theory, and experiments with lasers and beams. So this is very, very exciting, and I want to convey to you some of the directions that we've been exploring. The fundamental, I would say that the fundamental tool to address many of these scenarios from a simulation point of view in support of theory and experiments are particle in cell simulations. And on particle in cell simulations, we solve Maxwell's equations on a grid, and we follow self-consistent charge and currents due to the charge particle dynamics. This is a very old technique in plasma physics. This was pioneered in the 1960s by John Dawson and Oscar Bunneman, and it's very simple. So the only approximation that we are doing is solving Maxwell's equations on a grid. What has been exciting in the past 20 years is the ability of combining particle in cell simulations with very large supercomputers and take advantage of all the computer power that is now available worldwide, and also the possibility to expand the particle in cell algorithm to include additional physics that allow us to capture these extreme scenarios. So the physics is quite simple. It's very few approximations, and so this is really an amazing tool to capture some of the finer details of the dynamics associated with these scenarios. Let me just state that we've been making a strong effort to not only develop very sophisticated particle in cell codes that I'll show you some examples, but also develop numerical simulations, particle in cell simulations for education. And just in the last few years, five years, we've developed, my colleagues Ricardo Fonseca and Jorge Vieira developed this ZIP-PIC educational code suite that is an amazing tool to teach plasma physics and to test many fundamental ideas that we are going to discuss. Some that we are going to see here. Actually, under Laserlab, Ricardo Fonseca and Jorge Vieira they ran a particle in cell training camp based on ZIP-PIC, and this is readily available for the community to use and to explore with the significant support in terms of available notebooks to support teaching in plasma physics. Of course, we at IST we've been strongly involved in the development of Osiris, which is a particle in cell code that runs on big machines. This is developed in collaboration with UCLA, and much of what I'm going to show is based on Osiris, but let me just state that there are other codes that can reproduce similar features of what I'm going to show. So this also shows how vibrant the field is. There are many groups and many different codes exploring similar physics and similar scenarios. The exploration of these extreme conditions associated with the very high with extreme light, as we can trace back to the early papers of John Kirk and collaborators in 2001, 2010, where they started to look at the possibility of combining electromagnetic fields, for instance, from lasers to generate pairs. So this is a kind of the genealogy of this coupling of QED physics with particle in cell codes. There have been a number of groups that have been slowly progressing in coupling these exotic physics with particle in cell codes, and this is now something that is very well established. And the fundamental idea in particle in cell codes is that we have particles moving on a grid. As I just shown you, we advance these particles with the Lorentz force. We deposit their current on the grid. We solve Maxwell's equations and on the grid, and then we interpolate the forces back on the particles, and then we move back and forth. Of course, when we add extra physics, for instance, quantum electrodynamic processes, for instance, strong emission, strong radiation, we need to take into account that radiation can change the dynamics of the particles. So we need to modify the force that is acting on each particle according to the momentum that is given to the new particles. These new particles need to be added to the simulation. For instance, if we are radiating strongly, we are injecting photons on the simulations, and we need to follow these photons. And eventually, these photons can even interact with other particles or interact with background fields and generate new particles. If these new particles carry charge, electric charge, then this charge needs to be deposited on the grid. So there have been this is now becoming very standard. Many PIC codes follow this strategy, and I advise you to look into this review that follows, that covers most of the techniques. What I would like also to highlight is that one of the critical things is that, as you imagine, as soon as we start to generate new particles, as soon as we start to have these processes, and if we are looking at, for instance, cascades, like I'm going to show you next, what starts to happen is that in terms of the memory in our machines starts to be filled up with new particles, and eventually at some point we need to start to group these particles in a smart way. And this was a critical advance that was pioneered by Marija Vranić, where she found out what was the best way to actually do this in particle in cell simulation, and this has been critical for many of the advances that I'm going to show you. What is interesting, and some numbers that we need to take into account, is that we are really on the transition for the emergence of relativistic quantum behavior with intense fields. The critical number here that many of you have read about and learned about is the Schwinger field, and this is just a huge field. And if we look at for instance, the pair creation probability, we see that this is a tunneling-like probability that scales with the inverse of the Schwinger field. So in the sense, if the electric field overcomes the Schwinger field, at some point we go through this tunneling process and we have a copious generation of pairs. With these numbers, this would be extremely hard to reach in the laboratory. But if we think that this needs to or can be generalized for any Lorentz boosted frame, this chi parameter, that is essentially the ratio of the electric field to the Schwinger field, and that is also what is popping up right here. If we generalize this for any Lorentz frame, we see that if we have particles moving with a relativistic gamma factor, gamma with a significant gamma factor, the electric field in the rest frame of these particles are gamma multiplied by the electric field, the transverse electric field that they are feeling, and so we can actually reach electric fields in the rest frame of a relativistic particle, where this chi parameter starts to be comparable to 1. So what has been really transformational on this field of extreme light is the ability to start to consider relativistic beams or relativistic flows interacting with very intense fields, and for those conditions, chi can now become close to 1 or even be higher than 1. There are a number of QED processes that one can take into account. And what is exciting is that due to the systematic work of many researchers and many different groups, it's now possible to include all these processes in particle in cell simulations, and actually take into account for different initial conditions, different target properties, different laser intensities, a whole range of QED processes that are present in when we have these extreme light conditions. So I will, as I mentioned, I will focus on two research directions. So I've covered essentially the background in terms of the methodology that many groups use to study these conditions. extreme light, extreme fields, and their interaction with plasmas. So let me now give you two possible directions. The first one is essentially associated with ultra-intense laser and particle beams, and the other with QED processes in relativistic astrophysics. I don't know, I don't need to remind you about the critical role played by chirp pulse amplification that led to the Nobel Prize of Gérard Mourou. But this has been really transformational in terms of the physics regimes that one can achieve resorting to laser light. And I really like these type of plots because they show as a function of the year the focused intensity, and at the same time the physics that it's possible to explore with these intensities. What we've seen is that for the past 30 years, we've been seeing this exponential growth on the focused intensity, and at the same time we've been going from physics that is determined by Bowden electrons to relativistic optics, and in the near future, for sure, we'll be reaching these conditions of ultra-relativistic optics, where even the protons start to quiver in the field of the laser with the relativistic velocities. So this is very exciting, and along this way, there is many exciting physics and many exciting developments. I will just like to point out that similar intensities are also present in particle beams. And I really like to point this out because this really shows us that we are at the convergence point where many of these different subfields in physics come together and share similar physics, similar challenges. So I think this is very, very exciting. If we look at the intensities that are either already exist or are planned for particle beams, we see that the LHC, the intensity is 10 to the 19 watts per square centimeter, so 100 kilojoules in each bunch. SPS at CERN, 10 to the 18 watts per square centimeter, 7 kilojoules in protons. The ILC is predicted to reach intensities of 10 to the 24 watts per square centimeter, 1.6 kilojoules in the beams, and the slack beam, 160 joules, 10 to the 19 watts per square centimeter. So there's similar physics that can be explored with these particle beams and with lasers, and that is also relevant in astrophysics. And I will try to show you how, with some of these methodologies, one can explore all these scenarios. One of the key examples and one of the flagship examples of extreme plasma physics and extreme light applications is undoubtedly plasma accelerators, and they are really at the forefront of science. I mean, there are many examples of all the exciting advances that have been triggered by chirp pulse amplification in laser plasma accelerators. And this is really a combination of simulations, lasers, and novel plasma sources. And this has directly impacted this progress. And Laserlab teams have really made a significant contribution for all these exciting developments. At the core of these developments is laser wakefield acceleration. I always like to show this movie because this really captures the complex physics, but also all the exciting developments. So I'm showing a movie of a laser that is propagating into a plasma. The simulation window is moving alongside the laser. So it's like traveling along with the laser, and the laser is intense enough that pushes out the electrons. So it creates a void in the back, or a bubble, and this bubble is nonlinear. So what you see is that some of the electron trajectories are actually self-injected inside the bubble. This bubble, don't forget that this is an electron ion plasma, and so the ions are not moving, or moving very slowly. So there's a strong electric field that accelerates electrons in the forward direction and focuses the electrons in the transverse direction. So you see that the electrons are gaining energy because the color of the tracks is going from blue to red. So they are gaining energy, and they are also quivering transversely. due to this focusing field. As you can imagine, if we have relativistic electrons, if they have transverse acceleration, they are going to radiate, mostly in the direction of the forward direction. And this direction, and if they are relativistic, like in this case, they are reaching 150 MeVs, the radiation can be highly energetic. It can be X-rays, and in some cases, we can even think about reaching even higher energies. What is exciting is that, and this is one of the most exciting applications, is that these Betratron radiation, these X-rays, that in this case are called Betratron radiation, due to the fact that the motion that is leading to radiation is called the Betratron motion, is already producing very exciting results and very exciting applications. This is just images from a early work at Imperial College and at the Rutherford Appleton Laboratory of applications to explore the bone microstructure. For instance, this is not specifically here, but breast samples, mouse embryos, materials, shocks. So there's a whole range of applications of these X-rays that can be explored, and that have been there's just been a boom of applications and the development of these new X-ray sources. That is very, very exciting. One of the most exciting developments coming out of laser plasma accelerators in the past 20 years. There are also more fundamental developments, and one of the examples that I would like to share with you is the possibility to generate these exotic states of matter by creating electron-positron plasmas from the interaction of lasers and particle beams. So on these setups, we have the laser that is interacting with gas jet target. It generates a plasma, ionizes the gas, generates a plasma, and then it forms this bubble, accelerates electrons, and then the accelerated electrons, they are shot through a solid target, and by scattering the relativistic electrons on a solid target of IZ material, one can generate the gammas and the gamma rays, and the gamma rays in turn can lead to the production of pairs. And by carefully playing with the target thickness and then with the selection process, it's possible to create a plasma with almost the same number of electrons and positrons. And this is moving relativistically. So it's possible to study these relativistic fireballs. I would like just to point out that similar physics is now being explored at CERN. There's an experiment underway led by Gianluca Gregori at Oxford, where the proton beam is going to be sent in through lead converter. It's going to generate again electrons and positrons. The thickness of this target and the composition of the target needs to be carefully chosen, such that at the end we have almost the same number of electrons and positrons, and these are then sent through a plasma cell, and one can study the interaction of an electron-positron plasma with the background plasma and understand all the plasma instabilities. This is highly relevant because it's thought that the propagation of these electron-positron fireballs is at the heart of the emission in gamma ray bursters. So this is a key mechanism to understand magnetic field generation and radiation in some of the most extreme objects in the universe. And the ability to do these experiments and fine-tune our models is one of the most exciting directions at the focus of at the convergence of extreme intensities, either coming from lasers or from particle beams. In terms of exploring even more exotic configurations, there have been significant advances in exploring radiation reaction. This is radiation reaction is one of the most fundamental processes that one can look up in any textbook in classical electrodynamics. And this is really an exciting time because we are, again, as I mentioned, we are really at the transition from a classical regime to a quantum regime. And so these experiments open new windows into this emergence of quantum behavior in the relativistic regime for this particular process of radiation reaction. So the configuration is quite simple. Again, we have a laser that is generating a bubble. On the back of the bubble, we have an electron beam that is being self-injecting, that is being accelerated. And now we are going to counter-propagate another laser beam, and this laser beam is going to interact. Of course, it interacts with the plasma and the bubble, but the critical thing, this laser beam is going to interact with this relativistic electron beam. What is exciting is that there are significant differences if we look at the classical behavior and the quantum behavior of these electron beam. They're just transverse pictures of the momentum space on the interaction of the electron beam with in the classical regime and in the quantum regime, and we do see that evidence of the emergence of quantum behavior by this wider region in phase space. But what is more interesting, and this work by Marija Vranić really identified the path towards exploring this regime, is that there are clear signatures on the energy loss for the electron beam as it collides with the laser. And depending on the energy of the electron beam, so different colors here, and depending on the intensity of the incoming laser, we can easily predict what is the relative energy loss of the electron beam. What is exciting from my point of view is that we are really on the transition from regimes where chi, where this quantum parameter is lower or much lower than 1, and chi, which is comparable or higher than 1. Mari and other authors have explored the competition between the classical and quantum behavior, and so I would say that there is now a very good understanding of what will be the signatures of the classical behavior and the quantum behavior. What is exciting is that there are many experiments, I would not say many, but there are several experiments in several groups exploring these regimes. And these are just examples of the pioneering experiments that have started to look into this, at these fundamental processes of radiation reaction. The configuration is very similar to what I have described. There's a laser, two beams. One beam creates the electron beam, the other beam collides with the other laser collides with the electron beam, and one looks at the way that the spectra of the electron beam shifts. This is summarized here on this plot. Again, this is electron energy, these electrons per MeV, and these are the different plots when the colliding laser is on or off. So red or black, you see there is without laser, the energy of the electron beam is higher than with laser. So clearly the electron beam is slowing down from the collision with the other laser. And what these pictures from this paper here show are the different models to try to fit the data. And as you can see, there is still much room for improvement and for understanding, and I'm pretty sure that experiments and further theoretical work will be able to pin down what are the exact features that explain these spectra in these experiments. So this is a very exciting direction. Of course, what has been pushing forward many of these research programs is the eventual possibility to reach an even more exotic regime. And I really like to show this movie by Thomas Griesmeyer that illustrates in the most eloquent way what we are trying to achieve, which is the possibility to drive these QED cascades, including radiation cooling. So this is the most possible simple scenario where we have one electromagnetic wave colliding with another electromagnetic wave, and you have just one single electron in the middle. We are going to use very high intensity lasers. So A naught of 1,000, this is equivalent to an intensity of 10 to the 24 watts per square centimeter at 1 micron. So we are still a bit far from that, but one can dream. I think what is exciting about this simulation and this movie in particular, it shows the key physics and the key dynamics that one needs to consider, and the richness of the physics. So what we will expect to see is that the electron will start to quiver on the laser field. The acceleration is going to be so strong that it will start to radiate. It will radiate photons. These photons will show up in yellow, and then the photons themselves are going to interact with the background field, and so they will generate pairs. So, oops, let's see if I can play the movie. Okay, so here we go. So the electron starts to move in the laser field. It's accelerated, generates the pairs, the photons, and now the photons themselves, they interact with the background field, and they generate a cascade of electrons and positrons. Electrons in blue, positrons in red. As you can see, this is a very complex problem. So there's clearly an instability. There's also very complex dynamics on the way that these electrons and positrons are interacting with the laser field itself. So there's very rich physics. Just another example of how rich the physics is, and many different authors many different papers have been exploring what is the optimal configurations to generate these cascades, and even just to depict how complex the system is, just 3D simulations. I'm going to show 3D simulations again by Thomas Griesmeyer, where the only difference is the polarization of the lasers involved. Either linear polarization, the two lasers, double clockwise and clockwise, anti-clockwise. So if I play the movie, you'll see very clearly the significant differences in the dynamics, and what we are just changing is the laser polarization. So there are many different works exploring these different scenarios, and this is a very vibrant and exciting research direction that has been mostly explored, resorting to particle in cell simulations, with the hope that soon enough we'll have the lasers to start to explore these conditions. Here's another example of this type of conditions. So multiple laser pulses can more easily create the conditions for the generation of these electron-positron plasma, and so there are many different configurations, and the ideal configuration has been first explored in this paper, but this involves a 4-pi type of radiation. Other groups have been exploring using a finite number of pulses, and now we have a very good understanding of what are the key physics and mechanisms that need to be optimized, and what kind of plasmas can be generated and explored in these conditions. In many of these scenarios, we are still a little bit far from what is a plasma, and so one possible way is to actually instead of driving the cascades from a very small number of electrons, is to generate the cascades already within a plasma, so an electron ion plasma. So this is just one example where we have again two colliding laser pulses that are interacting with a solid density target, and the number of pairs that is created is strong enough to actually enhance the reflection of the laser, of the two lasers impinging on the target. And so again, there is now a very strong, I would say, quantitative and qualitative understanding of what are the conditions that are required to reach conditions where plasma physics starts to be important, and where the density of electrons and positrons starts to affect the laser dynamics, where this is really the conditions where we start to have plasma physics playing an important role. What I would like to also to highlight is that scenarios with beams are also of relevance. So on the interaction point of two particle beams, the electric fields can also be significant. So this chi parameter can be quite important, and in these conditions, what the critical number is what's called this disruption parameter. That I will give a very brief example of the different regimes that are determined by this disruption parameter. This is something that is well known from beam physics, but that shares many physics. There are many common physics with what can also be explored with the scenarios that I've been describing. And one example that I also like to highlight is that even the Betratron motion of ultra-relativistic beams created on the laser wakefield acceleration ion channel, the chi of the beam on these ion channels can also be significant. You cannot reach 1. This is very hard, but it can be a fraction of 1. And so we can on this transverse motion, the associated chi parameter can also be significant, and so this is another scenario where these strong radiation effects can also be important. Just to illustrate what the point about these different regimes in a collider, for instance, of electrons and positrons. If we are in the low disruption regime, the beams just go through each other and they just pinch a little bit. But there are very exciting regimes where they can pinch significantly, 1 or 2 times, like in this case, or they can pinch many times. And as you can imagine, when we have this strong pinching, we have strong radiation, and we have very strong fields, and we can reach conditions where pair production can be significant. We have explored the collision of laser wakefield accelerated beams to generate radiation in this low disruption regime, and we think that there are even more challenging and more nonlinear scenarios that can be explored when going into these regimes. This of course, is very challenging from a technical point of view. It involves very long particle beams, but nevertheless, this is something where there is clearly a connection between extreme light physics and beam-driven physics in the relativistic regime. Recently, we have also been involved in a paper that aims to explore an even more extreme regime of quantum electrodynamics by colliding very compressed and very high energetic relativistic beams, SLAC-like beams. But even with more extreme parameters, very small spot sizes, very high energies, also significant charge, and the goal here is to reach conditions where QED might break down. So there's a conjecture that states that the QED becomes a strongly coupled theory whenever this coupling parameter is comparable to 1, and so what many authors have been trying to address, both with lasers like in these papers and with relativistic electron beams like in this paper here, is can we really reach regimes where this transition in QED can be explored? So this is of course, these are fundamental questions, but very exciting from the exploration of these extreme light conditions. My talk is about extreme plasma physics, and one question that you might raise is how much plasma physics is present in these scenarios, or what is the role of the interplay between collective effects and QED. And we are still a little bit far from this, in the sense that if we want to explore plasma physics, our system size has to be our plasma size has to be on the order of the spot size of our laser, so a few microns, or the volume, corresponding to a few microns cubed, and within in this volume we need to have a few skin depths, a few skin depths, not only skin depths but also the violence. And if you plug in the numbers, this means that we need to generate pairs with densities on the order of 10 to the 20 per cubic centimeter, and this is a lot. This is not something that can be reached with present-day technology, but interacting intense lasers with very dense targets, or double irradiation, or even looking at the harmonics, we can start to see signatures for the presence of electron positron plasma behavior, which is really QED plasma physics. So very quickly, under which conditions are these extreme plasma physics of relevance? And in relativistic astrophysics, we find this in many objects, in particular in pulsars, but also in black holes. This is becoming a very hot topic. The magnetospheres of neutron stars and pulsars are very exciting objects. They have many different regions where many different physics is happening, but what is more interesting is that this is still an unsolved problem. There are many open questions on one end, and on the other end, there are electric fields and magnetic fields that are so extreme that QED effects do play an important role. So we've been, at the same time that we've been pursuing these research direction along the laser side, we've been also making connections with these type of setups and exploring what we learn from laser plasma interactions into relativistic astrophysics and vice versa. There is a dialogue here that can be explored, and that we've been trying to trigger in a more systematic way. And so in the magnetospheres of neutron stars, there are many different plasma physics processes that play a role. And just to show you what's the different regions and the different approaches, many groups have been looking at reconnection, magnetic reconnection, which has differences with respect to classical magnetic reconnection that we are all familiar in plasma physics. So we need to consider the relativistic regime, and even QED processes are important for neutron stars with very strong magnetic fields like magnetars. There are researchers looking at global simulations, trying to understand the global behavior, also doing numerical simulations. First without general relativity, and more recently including general relativity. And another focus of research is what happens at the polar cap. This is the region where the electric fields and the B fields can be so high that we have pair production, and so the dynamics here of pair of production of electron positron generation does have an impact on the radiation that is flowing out of the star. Just to give you an example, so this is magnetic reconnection is a classic problem in plasma physics. It's just an artist's impression of magnetic reconnection in the sun. And the challenge is to understand how the topology change in the B field, for instance, associated with the solar flare in this case, how this impacts particle acceleration and radiation. We've been making a significant effort in this. Kevin Schoeffler and Tomasz Grismeyer have worked significantly on this project with Dimitrius Zensky from the University of Colorado, and what they have shown is that there are qualitative differences between classical relativistic reconnection and reconnection in the presence of quantum electrodynamics effects with pair creation. And I will not try to guide you through all the details of the simulations, but just to show you the two movies to illustrate that there are qualitative differences that I can highlight here. So this is a standard type of simulation for magnetic reconnection, the classical Aries sheet type of setup. And the point here that I would like to highlight is that there are clearly on a QED type of scenarios, these magnetic islands or plasmoids, they are much smaller. And this is due to the fact that QED brings stronger cooling than in the classical relativistic case. This shows that there are differences, and these differences are also obvious again in the B field. You see here that these islands, these magnetic islands, I'm plotting here the magnetic field energy density, and the magnetic islands are much narrower in the QED reconnection than in the classical reconnection. This has consequences. This is what I would like to highlight here in the way that the energy is transferred from the fields to the particles is qualitatively different from the classical regime to the radiative regime, which is relativistic, but QED effects are not yet important, and to the QED effects. What you see is that the way that the fields exchange energy with the particles is qualitatively different in the three scenarios. And this has consequences. This has consequences on the way that particles are accelerated in these scenarios. And in astrophysics, it's critical the way the power law dependence on the electron spectra, for instance, is a critical measure. For instance, in the classical spectra, the power law is different from the QED, and also on the photon spectrum we see the same differences. So this is very exciting. It shows that there are scenarios in astrophysics where these QED processes play a role, and there are significant, there are important signatures that will be able us to identify in which regions these QED processes are playing an important role. I was planning to, I'm just running a little bit out of time, but I just wanted to highlight. So I've shown the reconnection. What is also exciting is what is happening in the regions of the highest B fields, the magnetic field lines in the polar cap. It's just an illustration showing that we have electrons streaming out of the surface of the neutron star, and as they stream out of the surface, they will populate the region, the polar cap region, with photons, electrons, and positrons, generating these cascades that we have seen also in lasers. This is very the physics here is quite rich, and there are similarities that many groups, and in particular Tomasz Grismeyer and other collaborators are exploring. So what are the similarities between the cascades in the lab and cascades in astrophysics? And there are several similarities that one can explore to develop and to progress on the understanding of these fundamental processes, both with lasers and in astrophysics. I will just skip this slide just to come to the conclusions, just to reinforce that there are many exciting frontiers in extreme plasma physics. There are several open questions, in fundamental QED processes in intense fields, and we now know how to express and benchmark those processes in plasma kinetic codes. So this has established a bridge between fundamental QED physics and fundamental QED processes and plasma kinetic codes, and this has been, I think, this has been very fruitful for these two communities. There are what I also hope that I've showed you is that there is very important applications that result from this work, namely on the optimization and configuration of secondary sources for gamma rays and positrons. This can have tremendous impact and tremendous applications, and there is now the know-how and the tools to optimize these configurations as we move to higher and higher intensities. And there are many radiation signatures of these collective extreme plasma physics processes that we can now explore in the laboratory, that we can now pinpoint in astrophysics. And one of the other very exciting frontiers that I didn't have time to discuss with you today is the coupling with GR. This is not so critical. Of course, it's not critical, not important for lasers, for pulsars as limited importance, but for black holes, where some of these processes are also relevant, is definitely important and central. And so this is a very exciting development on this coupling of extreme plasma physics, extreme light or extreme fields, and general relativity. So kind of as a take-home message, I would like to just state that the revolutionary computational power is really is reshaping our understanding of plasmas in extreme conditions. We can now explore multi-scale processes from first principles and with unprecedented detail. And this, we hope, some of these are already explored in the laboratory, and some of these we hope that will be soon explored with the new generation of ultra-intensity lasers, and others have astrophysical consequences. And this creates a very exciting topics for research at the interplay of simulations, theory, and experiments. And this is what I wanted to share with you. Thank you very much for your time and for having me.